Today we'll be talking about use cases in CockroachDB, specifically the IoT and device management use case, and how CockroachDB can help you manage a fleet of devices around the world. When it comes to this use case, consistency is critical. In this example, I'll be running a fleet of aircraft, and you can imagine what happens if data being reported on an aircraft is incorrect. In a system like this, eventual consistency actually adds complexity. You have to code around the fact that you don't know the true state of the data at any one time. You need to be sure that the world your devices are reporting is true to the real world. With a database that's always consistent, this isn't a problem you have to code around or develop against. You just read and write to it and can trust that the data is accurate. When you're running a fleet of IoT devices, be that aircraft, Alexas, and the like, they have to be online. They have to be available all the time. You can't take them down for planned maintenance, and your team need agility in making changes and adding new features to those devices when those features or fixes become available. These device fleets can be enormous in scale. A lot of major device fleets in the world contain millions of devices. And you don't want to have to be on the ground maintaining and manually sharding traditional RDBMS systems to cope with that scale. You want to add new nodes to a natively horizontally scalable database in order to keep up with that growing demand on your system. Traditional RDBMS systems like Oracle, MySQL, Postgres, including cloud service provider databases like Aurora and GCP for Postgres, for example, allow you to scale for reads, but they don't allow you to scale for writes. If you can't scale your database cluster such that your devices are close to the database node they'll be reading and writing to, let's say your primary node in a traditional RDBMS system is in US East 1, but your device fleet is primarily in Europe, by the time your devices have written their data across the pond, that data is probably out of date. These systems need to be secure. They might be handling incredibly sensitive data. CockroachDB support for SSO and MFA, RBAC, encryption at rest and in flight, audit logging, CMEX or customer managed encryption keys, and egress perimeter controls to prevent the unauthorized exfiltration of data will keep that data safe. For this example, I'll be simulating a fleet of aircraft that will be talking to a geographically aware load balancer for an application. I'm deploying the application on fly.io simply because it's easy for me to do that. I could deploy it on AWS, GCP, or Azure, but I'm choosing fly.io because I'm familiar with it. That in turn will talk to a geographically aware load balancer for CockroachDB, behind which will be a region in US East 1, EU Central 1, and AP Southeast 1, to ensure that there's always a region close to wherever an aircraft happens to be. I'm using Terraform to spin up the CockroachDB infrastructure. This will be a serverless cluster running across 3 regions, EU Central 1, AP Southeast 1, and US East 1, with EU Central 1 being the primary region. I'm creating a user called Rob with a randomly generated password, and that's the extent of the configuration for CockroachDB. I'll be consuming 2 main output variables for this example. One is the shell URL. This will allow me to access the CockroachDB shell without copy-pasting any sensitive information. And the other will be the IoT app URL. This will be used as an environment variable for the applications that will be simulating aircraft. Again, it means I don't have to copy-paste anything sensitive. I'll be seeding the database with random data. First of all, I clear everything in the database. Then I generate a bunch of aircraft. I generate a bunch of administrative information for those aircraft. And then I generate random aircraft diagnostics. These will update as the application runs, but I'm just seeding the data with initial positions for those aircraft. Along with the positions, there'll be a heading so that the aircraft can move along a given heading. The random aircraft will look like this. They're all random Airbus models with varying capacities, ranges, bases, and service durations. The application that will be simulating aircraft is going to physically run in Ashburn, Virginia, Frankfurt, and Singapore. And when it loads, it will fetch its local region from CockroachDB, and then it will use that to fetch all of the aircraft for that given region, iterate through them, and progress them along their heading. It will then update the aircraft in the database, and when the front end next requests the aircraft, they would have moved a little bit along their heading. The UI is very simple. I'm just using Leaflet.js to render a map, and then I'm loading the aircraft from the endpoint that will be generated by fly.io when I deploy my application. And then for each of the aircraft that I find in that JSON response, I'll iterate through them, clear the map, and add their new points. I'll create my CockroachDB cluster. And now I'll use the shell URL that was generated during the creation of the cluster to connect directly to the cluster. I'll create a database. I'll call it IoT for the example, whose primary region will be Frankfurt, along with the regions in Virginia and Singapore. I'll enable super regions as I'll be geographically pinning data to those regions. It's not advisable to create super regions containing just one region, as you'll lose quorum in the event of an outage. It's better that if you want to use super regions, you keep it to 3 or more regions within each of those super regions. But for now, for this demo, that's fine. I'll create a US super region for US East 1, an EU region for EU Central 1, and an AP region for AP Southeast 1. I'll hop onto the database and now I'll create some tables. I'll enable auto rehoming such that when an aircraft gets closer to one region than another, its home region, the region that the CockroachDB leaseholders will be in, physically move to that new location to be closer to the aircraft. I'll create the aircraft table, which will have an ID, model, capacity, range in kilometers, range in miles, which is simply a computed column representing the range in miles, calculated from the range in kilometers, a base, an operational since date, and a last service date. That's going to be a global table, meaning low latency reads from anywhere in the world. I'll create an aircraft administration table whose locality will be in Frankfurt. Let's say we only want to administer this table from the European region. By keeping this table in Frankfurt, we get low latency reads and writes to our administrative users. And finally, I'll create the aircraft diagnostics table. This is a regional by row table, which offers low latency reads and writes to the closest region, i.e. the region that the aircraft is currently closest to. This contains things like battery level, current location and heading, and I'll be using the heading to derive the CRDB region column, which will inform where CockroachDB needs to physically store that data. This is fairly contrived. You might want to go with something more advanced than this, but essentially I'm saying when the longitude value is less than -26, i.e. closest to the west, I want that data to be stored in US East 1. When the aircraft's longitude is greater than 44, I want to store that data in Singapore. Otherwise, I'll store it in Frankfurt. I'll seed those tables with the seed application that I showed earlier. And then I'll deploy the fly application. I'll create an application called CRDB IoT. I'll add an environment variable as a secret, which will be the connection string for the applications. They'll all share the same connection string, and that's because CockroachDB provides a global geographically aware load balancer. So if you use the same connection string, but you're based in Singapore, you'll be routed to nodes in the Singapore region. I'll build a Docker image and deploy the application. I'm not asking for high availability. I only need one instance of this application for demo purposes. And once that's deployed, I'll scale the application out so that it runs across 3 regions. With that up and running, I'll scale the application out to include Frankfurt, Ashburn, Virginia, and Singapore. With that all running, now I can open up my application and I'll start to see aircraft being plotted on the map. Let's focus on a couple of aircraft here. If I zoom in, you'll see that we've got an aircraft that's currently closest to the US region and an aircraft that's currently closest to the Frankfurt region. They're getting closer to one another and at some point they're going to cross over. This aircraft is currently seeing 5 milliseconds latency talking to the US node, and this one is seeing around 6 to 9 milliseconds talking to the Frankfurt node. So we'll let those aircraft get closer, cross over that line, and you'll see that their data is physically moved to the opposing regions because that's where they're now closest to. So we can see the aircraft that was closest to the EU is now closer to the US. Its data has been physically rehomed from Frankfurt to Virginia. And the aircraft that was closest to the US is now closer to Frankfurt, and so its data has been physically moved to Frankfurt. Both of these aircraft are seeing low latency reads and writes to their respective locations. If I hadn't rehomed the data, the latency would steadily get worse as they got further from their home regions. Remember, this is just a very contrived example whereby I'm using the longitudinal value to determine the closest home region. I'll tear down the infrastructure. So that was CockroachDB for IoT and device management use cases. This global use case would have been much harder to satisfy if it hadn't been for CockroachDB. It gives us the ability to not only scale horizontally, but scale across regions and pin data to those regions, making use cases like this trivially simple to implement and very quick to deploy. We deployed all of this infrastructure in a little over a minute. Stay tuned for more examples on how CockroachDB can satisfy your use cases.